Page 397, lesson 7.7 is on simulate compound events. So what we're going to talk about in here is how we can look at some events that might happen and how we could simulate the chances of them happening. So on 397 it says Jillian lands the beanbag in the hole about half of her attempts in a beanbag toss game. How can she predict the number of times she will get the beanbag in the hole in her next 5 attempts using a coin toss? So the reason we're using a coin toss is because she gets the beanbag in the hole about half of the attempts. Okay, so in flipping a coin, we have 2 options. If she's getting half of the time in the hole, half the time not, that's why that's going to simulate that happening. Okay, so what we could do is just basically label these one way or another. We could just say if it's, whichever we want it to be. Maybe if it's tails, then it's in the hole, and if it's heads, then it's not in the hole. And so if we want to simulate for 5 attempts, basically then we could just flip a coin 5 times and see what happens. Okay, and again, it's not a guarantee. You could just say, why don't they just throw the beanbags 5 times and see what happens? But it's just finding alternative approaches for simulating this. Look at example 1. Nikki is planning a hike for the end of the week. She really does not want to hike if it is raining the whole time, but it is okay if it is cloudy. Based on the weather forecast, should she postpone the hike? So here's what the weather's looking like. So each day you can see 40% chances of rain. So if we look at this, one thing we can do is develop a probability model. So it's either going to rain or not rain. So if it's a 40% chance of it raining, that basically means it's a 60% chance of it not raining. These are called complementary events. They add up to 100%. Or we could look at them as fractions. So 40% is 40 over 100, which is 4/10, which is 2/5. 60%, 60 over 100 is 6/10, which is 3/5. This is kind of what the book's using by doing this, because then in step 2, they develop the spinner. So this is a simulation, so it's trying to model or simulate what's actually going to happen. So in this case, we had 3 out of 5 for no rain. Those are the N's. We had 2 out of 5 for raining. Those are the R's. And what we could do then is spin the spinner and see what happens. So they did this simulation, and they looked at this and to see what would happen. So looking at this, there it rained, there it rained, it rained. That one it didn't rain at all. This one it rained one of the days. So it's just kind of a decision of what she wants to do. Technically, by the simulation, simulation, it never rained all 3 days. So you might say, well, if, it's not going to rain all 3 days, then maybe it's okay. Another thought process could be if you don't want to mess with it raining at all. Okay, so if she's hiking, she's staying for 3 days, I'm assuming then maybe she's setting up a tent and stuff. When you set up tents and things and it's muddier, it gets to be more of a mess. So she may want to just not mess with it, see if she can wait till another time when there's not as much of chance of rain. One thing we could do also, if she wanted to see what's the chance of it raining all 3 days, similar to what we've looked at before, is we've got a 2/5 chance of it raining each of those days. And so if we multiply those together, that's 8 out of 125. So technically, theoretically, if there's a 40% chance of rain all 3 days, there's only an 8 out of 125 chance of it raining all 3 days. Okay? For some reason, it seems like when there's at least a 40% chance of rain, then it rains.
Yeah.
But anyway, theoretically, if she is okay with it, as long as it doesn't rain all 3 days, then she might be okay. But again, if she wants to just hold off and wait for a time when it's not going to have as good a chances of raining, that might not be a bad idea either. So on the try it says there is a 50% chance the volleyball team will win any one of its 4 remaining games this year. So a spinner with 2 equal sections numbered 1 for win and 2 for loss is used to simulate the probability the team will win exactly 2 of its last 4 games. Results of the simulation are shown below. And again, they could have picked W and L for win and loss. They picked 1 and 2. Maybe they just had a spinner laying around that had this on it already. So whatever, this is what they're doing, so that's fine. Anyway, what we're trying to do is if they win exactly 2 of its last 4 games. So if they win exactly 2, remember the 1 is used for the win. So we're trying to look for things that have 2 1s in them. So 2 1s. I'm just going to circle the ones that have 2 1s. So we could say out of the 10 trials, there are 4. We circled 4 things, so there are 4 favorable outcomes. Again, for exactly, winning exactly 2, okay? So based on this simulation, the probability the team will win exactly 2 of its last 4 games is 4 out of 10, or you could reduce that to 2/5, or otherwise if you did that as a percent would be 40%. So either 2/5 or 40% would be acceptable answers for that one. And the convince me just mentions, does the probability change when exactly is replaced with at least? So if we talk about them winning at least 2 games, that's going to include where they won 3 games or maybe 4 games even. So the answer, yes, it does change the probability, because then now it would be 7/10 probability, or 70%. Example 2, the Hornets and the Tigers will play a 5-game series with the winner of 3 games named the state volleyball champion. The 2 teams are evenly matched. Use a simulation to find the probability the Hornets will win the 5-game series. So they're just doing either Hornets win or Tigers win. 50% chance, we're saying, because it's evenly matched. And so they did a simulation using a coin, flipping a coin, because it's 50-50 chance again. All right, and then they did a simulation. And again, if they win at least 3, then they win. So there they won 3, so they won. There they only won 2. There they won 3, so they win. Okay, so you look through this whole thing, then you can see what's happening. Some of these are kind of don't make a whole lot of sense, because technically once a team won 3 out of the 5, once you win the majority, then you'd probably just stop at that point. Okay, kind of like with volleyball sets or something, or with a series like a baseball series or something. You don't say, well, they won the first 4 games, but we'll just go ahead and keep playing all of them just because. They'll just go ahead and say that they won and move on. So anyway, out of this, though, the Hornets won 4 out of 7, which we might expect, it to be about half the time, since they're evenly matched. So example 3, an energy bar company is printing equal quantities of 6 different collectible cards. The company will randomly package 1 card inside the wrapper of each energy bar. What is the probability all 6 collectible cards will be packaged in a box of 10 energy bars? So this one, they're saying they're just using a random number generator. Another thing you could do, since there are 6 of them, you could roll a number cube. Rolling a number cube, 6 options there. Or you could spin a spinner that's got a 1 through 6 in it. Or you could put numbers in a hat that's got 1 through 6. Okay? We may not have access to a random number generator, but all of those would be things we could do pretty easily. So anyway, they did this trial. They did the trial 8 times. And you can see, actually, there's only one time out of the 8 that they actually got all 6 different cards. Okay, so like for example, trial 1, they didn't get a 2. Trial 2, they didn't get a 4. Okay, so you can look through, but anyway, it only happened one time. So 1 out of 8 times that they got a full set of cards. So they're saying it's a 1/8 or 12.5% chance based off their simulation. Obviously, the more trials you run, the more likely that would be to accurately predict what's going to happen. So if we would have stopped after the 3rd trial, you might have thought there's a 1/3 chance, but we just keep going. The question, maybe is, at what point do we know whether to stop or not? I would say probably it'd be good to do realistically maybe at least 10 trials. 10 would be even a good number, because then however many you get out of 10, let's say you get 2 out of 10, you just add a 0, that's a 20% chance. It's probably not realistic to do 100 times. Okay, 100 would be a really good number, but that's a lot of trials to have to go through to get to that point. So the try it in a tennis tournament, 25% of Sarah's serves were aces. Design a simulation to predict how many aces you expect Sarah to serve out of 50 serves. So they're not asking how many she's going to get out of 50. They're just saying they want us to design a simulation. So if we're actually working this out, figuring out about how many we would expect, we could do 25% of 50, so 0.25 times 50. We could work that out and get it to be, maybe 12.5. Obviously, she can't have half of an ace, so, say about 12 or 13 aces. But for simulation, designing a simulation, what we could do here is a spinner. And however you want to label this. But basically 25% is 1/4. So we'd have this spinner, and then it'd be like, 1 out of the 4 sections could be an ace. Another thing we could do, just as an idea, would be flipping a coin twice. If you flip a coin twice, you've got 4 options. And then you could just designate one of those, like say for example this would be representing an ace if we get heads twice in a row. That would be another way you could do that. The spinner is probably the easiest, most straightforward way to come up with that answer though. So the key concept again just talks about simulations, a way of modeling things to try to predict outcomes. So that could be spinners, number cubes, coins, random number generators. And again, we've talked about it already. The more trials you do, you're probably going to get closer to the theoretical probability of it actually happening. So if you look at the do you know how, number 4, Carl hits the target 50% of the time he throws a ball at it. Carl uses a coin to simulate his next 3 pitches. He assigns H for hit and T for miss. Results of 12 trials are shown below. Based on the results, what is the probability that Carl will hit the target with exactly 2 of his next 3 throws? So exactly 2 hits is what we're looking for. Okay, and again, that was pretty coincidental, right? H for hit, T for miss. I guess at least the H matched up anyway. So if we go through this, we can find the ones that have exactly 2 hits out of 3, exactly 2. And that would be 5 out of 12 would be our probability based off of that, their trials. Again, the more trials we do, the more accurate our result should probably be. And then if we look at number 5, on average, Margot scores a goal for her field hockey team 2 out of every 3 shots. Margot uses the number cube to simulate her next 3 shots. She assigns 1 to 4 as goals and 5 and 6 as missed shots. Why does the assignment of numbers on the number cube make it a valid simulation? So if she's making 2 out of 3, how does this work that she's assigning 1 to 4 as goals and 5 to 6 as missed shots? So the reason this works is 1 through 4, 1, 2, 3, 4, that's 4 options out of a total of 6 on our number cube. 4, 6, if you reduce that, it is 2 out of 3. And it said she made 2 out of 3 shots. So even though originally you're looking at the numbers, 4, I don't see a 4 anywhere. Well, it was 4 out of the 6 choices, and that reduced though to what we had, 2 out of 3 chance. So sometimes you have to consider that option as well. Obviously we don't have like a 3-sided object. We could do a spinner, okay, make a spinner with 3 equal sections and do it that way. But if we're going to use a number cube, that would be the way to do it. So on page 401, if we look at number 6, it says Molly makes 70% of her free throws. The random numbers below represent 20 trials of a simulation of 2 free throws using the numbers 0 through 9. So we're going to have to decide about what numbers we're going to use for a successful free throw and for a missed free throw. Okay, so we're going to keep in mind she makes 70% of her free throws. And so if we're using the numbers 0 through 9, let's think about how many different options that is. So 1 through 9 would be 9 numbers. If you just count it out, 0 through 9, count them out, you have just enough fingers. That would be 10 options. So if she's making 70%, what we can do is maybe think about how many out of 10 should be representing a made free throw. So that would be 7 out of 10. So if we wanted to, if you want to start at the beginning, starting at 0, and count out 7 numbers consecutively. So that would end at 6. If you count it out, think about it, 0, 1, 2, 3, 4, 5, 6. That gives us 7 numbers. Okay? And then the rest of them would be missed free throws. So that would be 7 to 9 would represent missed free throws. And then it says based on the simulated results, the probability she makes both free throws. What we would have to be doing then is looking at all of these numbers. Each of these digits, each individual digit represents her making it or missing it. So now we've got to look at all the numbers and look for ones where both numbers are between 0 and 6. So 21 would be one that works. The 2 and 1, both of those are between 0 and 6. 0, 3 down here is another option that works. 0 and 3 are both between 0 and 6. 5, 0 works. 4, 2 works. 6 and 6 works. 6 and 4 works. And that should be all of them. So if we look at that at this point, count them up, that's 6 out of 20 total. So 6/20ths. We can reduce that to 3/10 or 30%.